Hello everyone. In the last class, we have seen the basics of synchronous machines. After that, we have seen the winding configurations, EMF equation derivation. Later, we have seen the expression for voltage. So now we will be talking about the methods to find out the voltage regulation. So actually, there are basically four methods of voltage regulation. The first one is the synchronous impedance method. Second one is the Ampere turns method. And third one is a ZPF or Portier triangle method. The last one is the ASA method. Let's see the first method, that is synchronous impedance method. Impedance method. So in this method, the entire voltage drop is assumed as a drop due to armature leakage reactance. So earlier we have seen an expression for induced emf. Is given as E is equal to V plus IARA plus J times IAXL plus J times IAXA. This is a leakage reactance, this is the armature reactance, this is the armature resistance. Synchronous method, so the entire voltage drops. So voltage drop is nothing but E minus V. The difference is assumed as a drop due to the only armature leakage reactance, that is due to accelerator. This method, let us using this method. If you find the voltage regulation using this method, 100. So using this, if you find the voltage regulation, we will be getting the voltage regulation value greater than the actual value. So and this method is called as a pessimistic method. And the second, this is the first method. And the second one, we have the Ampere current method or MMF method. MMF method. So here in this method, the drop due to leakage reactance is considered as a drop due to additional armature reaction. So this method also requires OCC and SIC characteristics. So here, first actually they will find out two field. One is IFM, the other one is IFA. So IFM is a field current corresponding to the field current which is required to produce the rated voltage under open circuit characteristics. Now IFA is a field current which is required to compensate armature reaction under short circuit conditions. If we got IFM and IFA, then they will find out the resultant field current IF, which is a vector sum of IFM and IFA. So once we got the field current, resultant field current IF, so from OCC, from open circuit characteristics, they will find out. So this is the field current, this is the induced EMF, right? So once we got resultant field current IF, they will find out the induced voltage from OCC. So once we got the induced EMF, we can find out the regulation using expression E minus P by V into 100. So this gives voltage regulation less than the actual value. So this method gives voltage regulation less than actual value. So hence this method is called as an optimist method. So this is what I have discussed in the earlier slide. So let's see one example. Yeah, put that here. Okay, maybe I'll write it down for you. Okay. Sure. So a star connected 400 volts TH over pole synchronous machine has the following results. One is open circuit result, the other one is short circuit result. So open circuit result is VOC equal to 400, field current IF equal to 0.3 amps. Short circuit characteristics, short circuit current ISC equal to 10 amps. Field current IF equal to 0.5 amps. They're asking us to find out the per phase synchronous impedance at rated voltage. They have given us. They have given us open circuit voltage is 400 volts, corresponding field current is 2.3 amps. They're saying with 1.5 amps of field current, they are able to get the short circuit current. Now for 2.3 amps of field current, what will be the short circuit current? So X equal to 10 into 2.3 by 1.5. So this gives us 15.3 amps. Let us synchronous impedance can be given as you want per phase impedance, right? So per phase voltage that is 400 by root 3 by the short circuit current 15.3 amps. This gives you around 15 ohms synchronous impedance. Go to the next method, that is ZPF method. ZPF. In ZPF method, drop due to armature reaction as well as drop due to armature leakage reactance. That is XA and XL are considered separately. So this method gives voltage regulation near to actual value. So this method requires two characteristics. One is OCC, other one is the ZPF characteristics. ZPF characteristics are drawn between the field current and terminal voltage V at a constant armature current, comma, speed n. ZPF characteristics will look, this is the terminal voltage V, this is the field current. ZPF characteristics will start from here. This, let's say this origin and this point is A. So OA is nothing but field current corresponding to the short circuit condition. That from OCC, one more, right? This is OCC characteristic. This is ZPF characteristic. Let's say this is our rated voltage, B rated. There is one more line called air gap line. Air gap line is a line drawn parallel to OCC. Okay. Draw a point from here backwards to a length equal to OA. Okay. Let's name it as this point is B, this point is C. Now draw a line parallel to this line such that it touches the OCC at point B. Now complete the connect the other point, so we'll be getting a triangle. Now if you draw the perpendicular from B to CB, let's name that point as E. Here OA equal to BC, which is nothing but field current corresponding to short circuit condition, and CE is the field current required to compensate drop due to armature leakage reactance, that is XL. So the length BE gives us IF IFA, that is a field current required to overcome the drop due to armature reaction, and DE gives us the drop IAXL. So we know from the induced expression of voltage, E can be given as E is equal to square root of cos phi plus ARA whole square plus sin phi plus or minus IXL whole square. Now XL we have the field current, we have the terminal voltage. So from that we can calculate the value of E, right? Now find out, this is open circuit. Once we calculate E, then find out the field current corresponding to produce this induced voltage. Okay, once we have that field current, we have to compute the resultant field current. So once we got the resultant field current, we'll use to find out the induced EMF from OCC. So this method gives us the more accurate value of voltage regulation. Let's go to the next slide. So this is what I have discussed in the earlier slide. So ZPF method gives us the voltage regulation value close to the actual value. So in this method, drop due to armature resistance and armature leakage reactance are reaction are considered separately. Okay. Next one is the fourth method. It's ASA method. So in this method, drop due to saturation will also be considered. So in earlier methods, we haven't considered the drop due to saturation. In this method, drop due to saturation is also considered along armature reaction drop and armature leakage reactance drop. That is XA and XL. So this method gives us more accurate results out of all the methods. Okay. For example, let's take a method voltage regulation value. So let's say we have EMF method, MMF method, ZPF method, ASA method. Let's say our voltage regulation are 20%, 30%, 25%, 10%. Right? Now if EMF gives us the worst value, that is 30%. ASA method is more accurate than ZPF method. So ZPF gives us that 20% and ASA is more accurate, so it will be giving 10% and MF method will be around 25%. Okay. So the order is like EMF, MMF, then ZPF, and we have an ASA method, increasing order of voltage regulation. We have one more term called short circuit ratio. Short circuit ratio is defined as a field current ratio of field current required to produce rated voltage, let's say IFM. Open circuit characteristics to the field current required to produce rated armature current under short circuit current. So, okay, this is generally equal to 1 by ZS, synchronous impedance, and approximately we can write 1 by XS. Right? So SCR is inversely proportional to 1 by XS. This is a summation of XA and XL. So I can write SCR is inversely proportional to XA, which means, so we know that voltage regulation is proportional to armature reaction. Because armature reaction increases, the drop increases, because of which the voltage regulation increases. So armature reaction is proportional to XA. So armature reaction is inversely proportional to CR. So we also know that armature reaction is inversely proportional to air gap length, because if length is less, then the effect of armature flux on main field flux will be more. So both are inversely proportional. So armature reaction is inversely proportional to air gap length, that is inversely proportional to short circuit current. So when air gap length, so you can write air gap length is directly proportional to SCR, right? So if air gap length increases, machine becomes bigger, right? So cost increases. Let's try to solve one example question. So this is what I have discussed in the earlier slide. Okay, we'll see this question. So give 2017 question. A 25 kVA 400 volt delta connected three-phase cylindrical rotor synchronous generator requires a field current of 5 amps to maintain rated armature current under short circuit conditions. For the same field current, for the same field current, the offset voltage is 360 volts. Let the armature resistance and magnetic saturation, which voltage regulation percentage with respect to terminal voltage. Asking us to find out the voltage regulation. So when generator is delivering at rated load 0.8 power factor leading. Let's try to solve this question. So they have given us it is a 25 kVA 400 volts delta connected, right? The load current can be given as IL equal to 25 into 10 Q by root 3 into 400. So that is around 36 amps. Now the per phase by phase equal to I line by root 3. So that is will be around 20 amps. So they are saying to obtain this rated current, that rated armature current of 20.8 amps, the field current is 5 amps is required, right? And the same field current to maintain open circuit voltage also of 360 volts, they are also require a field current of 5 amps. You know that synchronous impedance can be given as open circuit voltage by short circuit current at a common field current. So it will be 360 by 20.8. So that is around 17 ohms, right? Now the induced EMF can be given as E is equal to square root of V cos phi plus IARA whole square plus V sin phi plus or minus IAXS whole square. So since it is a rated load 0.8 power factor leading, so we have to consider minus sign. Now we can substitute, right? V equal to 400 volt, cos phi is 0.8. Instance they haven't given, so you can consider it as a 0. And the sin phi is 0.6. IA is 20.8 amps. Excess we have 17 ohms. So if you substitute that, all will be get 341 volts per phase. Let's go to the next topic, that is two reaction theory. What is the two reaction theory? See, two reaction theory is applicable only for salient pole synchronous machines. Okay. Why? Because if you see the salient pole rotor, it looks something like this. So let's the four pole rotor we have. This is the stator, right? See here, the air gap is less, but here the air gap is more. So in cylindrical rotor machine, but if you take the cylindrical rotor, this is stator, where the rotor will also be the cylindrical position, and then we have some slots here. So the air gap is almost uniform, right? So in cylindrical rotor machines, air gap length is same along D axis and Q axis. Generally, This is called Q axis and this is the D axis. So the area of length is same. But if you take here along the Q axis area of length, if you take the 4 pole, for example, if a 2 pole machine, see the area of length, this is the Q axis and this is the D axis. So the area of length is less along the D axis and more along the Q axis. So therefore, in a salient pole machine, whereas in a cylindrical rotor machine, the area of length is same along D and Q axis. So that's why the armature reaction is because the area of length increases, the effect of armature flux, the main field flux increases. So the armature reaction increases. So in salient rotor machines, the area of length is minimum along D axis and max along the Q axis. So therefore, the armature reaction is maximum along D axis and minimum along the Q axis. So earlier we have seen, right, the armature reaction reactance. So armature reaction drop is represented by a reactance, that is armature reaction reactance. So earlier we have represented by single reactance value. That's okay for cylindrical machine. Whereas for a salient pole machine, it's not suitable because the armature reaction is high along the D axis and low along the Q axis. So we need two reactants. So one is the direct axis armature reactance, that is given by XAD. The other one is the quadrature axis armature reaction, that is given by XAQ. Generally, this XAD, D axis synchronous reactance, D axis synchronous reactance, that is XD, which is a summation of XAD, direct axis armature reaction reactance plus XL, leakage reactance, is greater than the Q axis synchronous reactance, that is XQ, which is equal to XAQ plus XL. Okay. So earlier we have seen the cylinder machine, right, where the expression for reduced indivisible B is equal to E is equal to V plus IARA plus J times IAXA plus J times IAXL. But now in case of salient pole machine, the reduced EMF expression is given by E is equal to V cos delta plus I IQRA plus or minus IDXD, XD, where ID equal to IA sin psi and IQ equal to IA cos psi. Okay. So this psi is a summation of two angles, that is delta plus phi. This is a lower power factor angle. Delta is the angle between E and V. It is also called as a load angle. So there is one more expression for finding out the psi, that is tan psi, which is given by V sin phi plus or minus IAX cube by V cos phi plus IAR. Okay, let's try to solve one example related to two reaction theory. So this is what I have discussed in the earlier slide. So try to solve this question. It's a GATE 2001 question. The direct axis and quadrature axis reactance of salient pole alternator are 1.2 per unit and 1 per unit respectively. The armature resistance is negligible. If this alternator is delivering rated kVA UPF and at rated voltage, then its power angle is. So they're asking us to find out delta. What they have given us, XD equal to 1.2 per unit, XQ equal to 1.0 per unit, voltage V equal to 1 per unit, kVA also 1 per unit. Earlier we have seen expression for cancer, right? Equal to 3 sin phi plus IARA by U cos phi plus IA IAXQ by IARA. So if we substitute the above values, we have V sin phi is 0 plus 1 into 1. Phi V cos phi is 1 into 1 plus 0 into 1. So this gives 1. So psi is 45 degrees. Delta plus phi equal to psi, right? Now delta equal to 45 degrees minus phi. Phi is 0. So that is 45 degrees. Phi because phi is 0 because it's a UPF load, unity power factor load. Let's go to the next topic. That's test. Test is used to find out the direct axis and quadrature axis reactances, which we have seen in the two reaction theory. Test. If test is used to find out XD comma XQ. So how to do this test? So in this test, generally the synchronous machine field winding. Field winding is open circuited and the reduced voltage is applied to armature. And the machine has to be driven at a speed less than synchronous speed, machine rotor. They'll keep a voltmeter and ammeter in the circuit. So when the armature MMF aligns with D axis, what happens is generally the ratio of voltage by current gives us the impedance, right? So XD is given by voltage max per phase by armature current minimum per phase. So XD is calculated when armature MMF aligns with the D axis. And similarly, when armature MMF aligns with the Q axis, we'll get a value of quadrature axis reactance that is given by V min per phase by IA max per phase. So the single voltmeter trigger ammeter. So the maximum reading and the minimum reading they will take down from the two meters, and then they will calculate the XD and XQ. our point is during slip test, so the car is open circuit and it is stator is connected to the supply. So there will be an flux produced by the stator winding. So since the rotor is rotating in that stator flux, there will be an EMF induced in the rotor, and that EMF induced is of AC. It is at slip frequency. Let's go to the next topic, that is power flow equations. In derivation here. So this is what I have discussed in the earlier slide. So let me draw power flow equations. So let me draw the circuit diagram. We have a synchronous machine. The induced voltage is at the Z angle delta. And then we have a synchronous impedance ZS. And this is connected to load L. And this is the armature current IA. This is the terminal voltage V at angle 0 degrees. Now I can write E is equal to V plus IA ZS, right? So IA is equal to E minus V by ZS. So IA can also be given as E at angle 0 minus V at angle, sorry, E at angle delta minus V at angle 0 by ZS at angle theta. IA conjugate is given by E by ZS at angle of delta minus theta minus V by ZS at angle theta. We know that S equal to P plus JQ, that is equal to V into IA conjugate. So this I can write V at angle 0 degrees into A by ZS at angle delta minus theta minus B by ZS at angle theta. So if you separate the real and imaginary term, equate them both on both sides, we'll be getting the expression for V as EV by ZS cos theta minus delta minus V square by ZS cos theta, sorry, cos theta. And similarly, the expression for Q is given by EV by ZS sin theta minus delta minus V square by ZS sin theta. So where theta equal to tan inverse XS by RA. So if theta equal to 90 degrees, which means over there is only the real part, there is no imaginary, only armature resistance is present. Sorry, armature resistance is absent, only the reactance is present. Then we can write P equal to U by XS sin delta and Q equal to V by XS cos delta minus V square by X. So, and condition to get maximum power in this case is theta equal to delta equal to theta. This expression you can obtain by derivating power with respect to delta and equal to 0. Okay. This is for a cylindrical rotor machine. These expressions are. For a salient rotor machine, the expression for P is given by EV by XD sin delta V square by 2 into 1 by X cube D into sin 2 delta. Okay, we'll see one example problem. So this is what I have discussed in the earlier slide. Let's try to solve this question. It's year 2014 question. A synchronous generator is connected to an infinite bus with excitation voltage equal to 113 per unit. The generator has a synchronous reactance of 1.1 per unit and is delivering real power of 0.6 per unit to the bus. Assume the infinite bus voltage to be 1 per unit, neglecting stator resistance. The reactive power Q in per unit supplied by the generator to the bus under this condition is. So what they have given? Field EMF is 1.3 per unit. Access is 1.1 per unit. Power 0.6 per unit. Per unit. That the expression for P equal to V by access sine delta, since R is not given. So P is 0.6 equal to E is 1.3, V is 1.0, by access is 1.1 sine delta. If we solve this expression, the value for delta is given by 30.5 degrees. Reactive power Q is given by V by access delta minus V. It is 1 by 1.1, 0.3 into cos 30.5 degrees minus 1. So if we solve this, we'll be getting 0.108 per unit. Guys, that's all for our today's session. We'll continue in the next session.